Welcome. Obviously, generating bioenergy needs feedstock. In this module, I will present bio-based feedstock suitable to be used as a source of energy. Let's start with the most simple way of producing bioheat. You all know how enjoyable heat when burning wood in a campfire or fireplace. Also on industrial scale, wood and woody biomass are used as sources of heat, often combined with generating electrical energy. In Brazil, for example, bagasse, the waste material from sugarcane after squeezing out the sugar, is the main energy source in processing sugar and bioethanol. Here you see a photo from a so-called usina, a Brazilian sugarcane refinery. Please note that this is a model example, how the energy content of biomass and its potential for material use, in this case ethanol, supplement each other in running a biorefinery. Also in Europe, woody biomass feeds combined biomass heat and power stations. Residual timber, demolition wood, but also wood chips, even imported from Canada, are used in Europe. This photo here shows a combined biomass heating and power plant in Bavaria, Germany. Woody biomass is the preferred feedstock in heat generation because its energy content is relatively high, much higher indeed than non-woody biomass. This is because of its low water content and high density, making it also a material easy to ship. Wood can be used directly with only little pre-processing, but other fuels need to be produced by complex processes. Biofuel are liquid or gaseous energy carriers. As you can see in this table, we distinguish between two types of fuels. Those starting from carbohydrates, as shown on the top, and other starting from vegetable oil, as listed in the middle. Furthermore, we differentiate between feedstock harvested directly from the field and processed to give carbohydrates or oil, and, please have a look on the lower lines, materials and residuals generated along the processing chain of biomass and the usage cycle of bio-derived consumer products. For example, bagasse, mentioned earlier, or straw, or press cake from pressing vegetable oil, or residual wood in forestry, are agricultural and forestry side products. Also, waste materials, after ending the usage cycle of a bio-based product, can enter the production cycle again. This might be a cotton cloth or a bio-based plastic bag collected in your waste bin at home. Suitable are also used cooking oil, sludge from wastewater treatment, or manure from animal breeding. Even gaseous carbon sources like CO2 or carbon monoxide provide a feedstock option. Given the suitable transformation technology, all these materials can be converted into different fuels, such as bioethanol, biodiesel, biomethane, and hydrogen. These are the examples we will discuss further. Well, let's begin with bioethanol, a biofuel added to fossil-based fuel in Europe and worldwide. Bioethanol is predominantly made from sugar, a biomolecule available from a large variety of plants and residual materials. The first line shows sucrose, a sugar produced in Europe, especially in northern France, Belgium, Netherlands, Germany, and Poland, through the cultivation of sugar beet. It accumulates up to 20% sucrose. Alternatively, sugar cane is grown in tropical and subtropical areas like Brazil, India, and Southeast Asia. The sucrose content in sugarcane is a little lower, but with 15% still impressive. Sucrose is a disaccharide consisting of glucose and fructose, both sugars with 6 carbons and easily metabolized by yeast. As shown in the first line, sucrose is extracted from the biomass and can ferment it to give biofuel. The second line explains ethanol production from starch. It is produced by a variety of starch crop cultivated in subtropical and moderate climate zones. Grains like wheat, rye, and barley are cultivated in Europe, triticale in Canada, and corn in the US. These crops contain between 52 and 65% starch, a polysaccharide consisting of a chain made from glucose. Another important starch plant, especially in Northern Europe, is potato, providing up to 18% starch. Before microbial fermentation to biofuel, starch is hydrolyzed to glucose, which again can easily be fermented to bioethanol. The third line shows another source of fermentable sugar. It is lignocellulose, coming with agricultural waste streams like wheat straw, corn cob, rice husk, bagasse, empty oil palm fruit bunches, but also residual wood, sawdust, and even used paper provide feedstock options to fermentable sugar. Lignocellulose is the main component of plant cell walls, thus representing the most abundant natural polymer. Together with hemicellulose and lignin, it forms a complex and rigid structure allowing plants to build highly stable structures like straw and wood. Cellulose consists mainly of glucose. Hemicellulose comes with so-called C5 sugars like xylose, arabinose, containing 5 carbons. Both C5 and C6 sugars can be used to produce bioethanol, thus in principle making any plant material a suitable sugar source. All these materials, and even carbon monoxide and carbon dioxide, as mentioned in the lowest line of this table, can give bioethanol. The energy content is 510 kilo oil equivalents per cubic meter. Please note that lignocellulosic materials are not eatable and therefore classified as non-food biomass. Biodiesel is made from vegetable oil. Primary agricultural sources are crop like soybean in Brazil and the US, canola in Canada, rapeseed in Europe, and palm oil in Southeast Asia, especially Malaysia and Indonesia. In Eastern Europe and Russia, also sunflower and gold of pleasure deliver an important share of vegetable oil. Oil crop are available from any climate zone. All these plants produce eatable oil, but in the case of biofuel, also non-food sources should be used. Algae provide an option for non-food biomass. Some species accumulate extremely high oil levels. Another alternative is animal fat, which is produced as a side stream by meat industries. Also, used cooking oil is an option. From a technical point of view, all these bio-oil sources are suitable, but for the time being, soy, canola, rapeseed, and palm oil dominate the markets. The energy content of biodiesel is high. It is, as shown here, 780 kilo oil equivalents per cubic meter. Today, the most important oil-based fuel is biodiesel, driving passenger cars and trucks. However, also the aviation industry is seeking biofuels to replace kerosene, and the shipping industry to substitute bunker oil. The very same feedstock as for biodiesel can deliver biokerosene as well. Fossil-based methane is a very well-established energy source and fuel. Produced as natural gas, it is easy to ship through pipelines and as a liquefied gas per ship. Its bio-based counterpart is biogas, containing an average 60% methane. This molecule is a starting point for a variety of applications. By burning, it generates heat and electrical energy. Purified to biomethane, it can be used as fuel to drive cars and trucks. And, just to mention it, methane is an important adduct in chemical synthesis. Not only the end uses are wide-ranging, the same is true for the feedstock portfolio. Biogas, as is shown on this table, can be produced from any non-woody vegetable biomass. In Germany, for example, primary biomass like energy corn is cultivated to feed biogas plants. Biogas fermentation also accepts food waste, industrial organic waste streams, organic municipal waste, oil and fat and manure. Biogas is therefore an important step in recycling biomaterials and, considering the high energy content of 510 kilo oil equivalents per cubic meter, it is a suitable energy storage molecule. Because the scale of the plant is limited, biogas fermentation is the technology of choice in a decentralized infrastructure, for example, in rural areas. Synthesis gas is currently produced from coal, mineral oil, and gas. However, synthesis gas can be produced from any organic material, including biomass and bio-based solid, liquid, and gaseous waste streams. As you can see in the second line of this table, all the materials mentioned earlier, especially industrial and municipal bio-based waste streams, provide feedstock options. These materials are gasified, and the resulting synthesis gas can generate heat and electrical power of 780 kilo oil equivalent per cubic meter, and in addition can be converted to biofuel such as methanol and dimethyl ether and more chemicals. The synthesis gas technology is more suitable for large scale and therefore advantageous in industrial and municipal centers. Hydrogen is another promising energy carrier and fuel. Here you see a picture of a hydrogen-fueled train in Germany. You may wonder why hydrogen is mentioned here in the context of the bioeconomy. In fact, hydrogen will play an important role. Firstly, it can be produced from bio-based hydrocarbons the same way it is provided from fossil resources today. And secondly, hydrogen is a reactant needed in reducing CO2 to biomethane. This slide shows a fermenter, a vessel to run fermentations, the basic technology of processing many of the feedstock I have presented so far. Well, all fermentation processes come with an unavoidable loss of CO2. In fact, biogas plants and aerobic fermentation emit a high concentrated CO2 stream mentioned. However, emitting CO2 can be avoided. It can even be used as a carbon source. When feeding hydrogen and carbon dioxide to anaerobic fermentation leads to methane, ethanol, and more fuels. So, CO2 turns into feedstock. In summary, we see that heat, power, and fuel are available from bio-based feedstock. The right table shows examples of bioenergies, their production volume and share. Bioheat already reaches a share of 24%, but bioelectricity and biofuel still have a share of only 3 to 6%. This compares with high volume feedstock options listed on the left table. Agriculture and forestry products and residuals are available in the million tons range. Especially lignocellulose from woody biomass, such as straw and bio-waste, are available in very big volumes. Primary biomass, like sugar and vegetable oil, is established in bioenergy and will continue to provide a solid energy base. However, when developing the future feedstock portfolio, residuals and waste materials will gain relevance. These materials are currently not completely utilized, and in addition, their utilization doesn't compete with food and feed applications. Especially residuals will therefore see a sustainable future growth potential in generating bioenergy.